We're now going to skip to section 4 of the notes, basically. We'll go back to section 2 if possible, if we have enough time to talk about ELF format. But I want to make sure that we at least get through the virus lab and the UPX lab. So, the point of these labs and this miscellaneous stuff here at the end of the section 4 things are to start giving some practical examples of how knowing information about the binary format can be used by malware, and in turn is necessary that you know it in order to understand what malware is doing. So we're going to talk about viruses only in the sense that we're going to define them as being programs which self-replicate needing human interaction. So I define a worm as anything which can self-replicate without human interaction, and a virus needs human interaction. So that could mean walking around with floppy disks in order to spread it around to different systems. That could mean, if you need to double-click on an executable in order to launch the Trojan, which then, sends out email to the other people who then double-click on the executable to send email to other people. I call that an email virus, not an email worm, because it required a human in the loop. So we're going to specifically be talking about viruses that infect PE files, though. Theoretically, we'd also talk about ELF, but I don't have a convenient teaching virus for ELF at the moment. So conceptually, this is what we've been dealing with. We've got some binary file. We've got our PE headers up there. And then we have, some number of section headers. And then we have the data for the actual sections. And so one thing a virus can do is it can just tack itself onto the end of the file. And then it can say, OK, well, these headers, originally they pointed into the .text. So this would, in our case, be on a PE file. This would be the address of entry point, right? The address of entry point specified some RVA which pointed into the .text section, because that's where all the code is. So what the virus can do is they can tack themselves onto the end of the code and redirect it so that the very first thing that executes when the OS loads this up is the code pointed to by the address of entry point. And that address of entry point will point at the virus. Right? And there's various design decisions the virus writers can use. Right? So if the original was that, and if there happened to be some padding here, so back when we were talking about, file alignment and section alignment and stuff like that, we said there could potentially be padding between things due to, if you're, let's say instead the padding was in the .data section, if you only had 4 bytes of data, then you would still have to have hex 200 bytes worth of overall stuff written to file. So theoretically, a virus could put itself in some padding space and then just make sure that it gets loaded into memory, change over the headers to say, execute my virus code as the first stuff you execute. And then just an alternate thing is that I feel like some early antivirus heuristics looked for things like modifications of the .header section. So on critical like system fields and stuff like that, where they could check against, this is, whatever, some critical system thing, blanking here, kernel32.dll, something like that. They could say, I know that kernel32.dll always points into the .text section, and it always points at some offset. If the attacker had modified the headers to actually point where they don't point normally, like in this previous example, some antivirus heuristics would find that. So instead, the malware leaves the headers pointing exactly where they normally point, and then they just put in like a jump instruction immediately at that location. So point wherever it's going to point anyways, and then jump immediately to the virus code. Jump back to the original code when you're done. So specifically, our virus in the virus lab today is going to be of this form. So it's just going to tack itself onto the end of executables, and it's going to modify the headers to point at itself. That's a null slide. And so the interlude is that I was sitting around thinking, how can I actually write this virus code so that it can open the files and write to files and things like that? Because, all right, so think about this from what you know about PE format at this point. If I write some code, which I'm just going to blob onto the end of some other executable file, if that code uses something like create file, which is actually how you open files, and write file, which is how you write to files, so if I just compile this code with a compiler, that call to create file is going to be trying to call into some import address table, right? And so unless I also have with my virus some import address table, which I keep around with me, that wouldn't work. But even if I have an import address table that I keep around with me, who's going to fill it in, right? So how is the operating system going to know to fill in the function pointer for create file if I just have some virus code tacked onto the end? So this sort of leaves the virus writer with a problem here in terms of if they want to call any library functions from printf to, just open file, right? A virus needs to be able to open files and write files because otherwise it can't self-propagate. It can't write itself to the next file that's the victim. So it turns out there's a good solution for this on Windows. And so Corey reminded me that there's this paper by Scape about searching for functions in the export address table. So you manually will go search the export address table for kernel32.dll. And by searching that table, you can find all the things you need in order to write yourself into other files. So specifically create file, write file, etc. So you can go look at the shellcode paper, and this will tell you how attackers who inject themselves into processes can find things like open file, close file, whatever. But we use the same technique in order to actually write position-independent code which is able to use library functions, even in the absence of the operating system figuring out where things are. So this is baby's first page. So like I said, it is like the picture one where we just tack ourselves onto the end and we redirect the headers. So the caveats with this code are that it can only infect binaries in C:virus target. That's to make sure that it doesn't spread to places we don't want it to spread to. Furthermore, for safety purposes, we have a kill switch built into it so that the parent virus, we'll say the very, first virus, the very first virus can infect, some number of files. Those children viruses can infect files, but the grandchildren viruses cannot infect files because basically there's just a counter that each of them updates when it infects another file. And so when that counter gets to be greater than 1, the viruses just terminate themselves and they say, I can't run because my counter is greater than 1. So the initial thing has a counter of 0. When it infects the first file, it sets the counter to 1. So the first file checks its counter and says, oh, my counter is 1. I can infect stuff. And it sets the counter of the infected grandchildren to 2. When the grandchildren run, they say, my infected counter is greater than, my kill switch counter, rather, is greater than 1, so I'm not going to execute. I'll just go to the original code as it was. And further further safety check is the fact that this code, it started out as just a incorrectness of the code, and then I am now calling it a safety check, is that the virus, when it infects the binary, it doesn't fix the checksum, and therefore it's not actually running. And so you need to use CFF Explorer to fix up the checksum on the infected file before the infected file will run. And once that runs, then it can go ahead and infect other files. So again, it doesn't do anything malicious except for copying itself to the end of all these files. So let's walk through this lab now. I want to open up Visual Studio as before. You're going to want to right-click on baby's first page and set that as the startup project. So then it should be bold. If you go all the way to the bottom of baby's first page, you'll see the main, which is the thing which actually kicks off the first infection. So the initial stuff doesn't really matter that much. You can go read that later. The point is that it eventually calls inject me. And the inject me code itself, that is almost the entirety of the code which gets copied over to the other files. So inject me is the primary body of the virus code. So Matt will compile the hello world.exe in a second here separately, and then we'll copy that over to the virus target thing in order to infect it. And you may have changed the, oh, so yeah, we'll see in a second. It probably is going into a different into a different folder than you're expecting. So we'll see in a second, and if it doesn't work once we get there, then let me know. All right, so if we right-click on inject me and go to definition, this is the majority of the code right here. Now, Bill, can you go over to the board? A high-level sense of how this, how the virus is structured. It basically has a little bit of helper data at the beginning that it assumes will always be there, and then it's followed by the code. So how the overall virus works is that at the very beginning we have this, I believe it's the very beginning, yeah, is the kill switch. I think it's called kill switch counter in the code. So we have kill switch, and what this is it's actually all the way up here. So we have this special data right here that I've declared, and I've just emitted some 0 bytes. So I just said, okay, put 4 bytes of zeros there, put 4 bytes of 0 there. The special data, the first 4 bytes are the kill switch counter, and the second 4 bytes are the original entry point. So the kill switch counter on the parent virus starts out at 0, and the original entry point, so original entry point, this starts out as, in the parent virus, it's a little special case, but basically it starts out as the address immediately after inject me, so that it starts out as return to here, basically. So this code right up here, it just copies that return to here into the special data, so that when inject me is done, the point is when the virus is done, it needs to go call to the original entry point of the executable, right? So if Notepad would have originally went to a certain offset, but the virus redirected it to the virus code, when the virus is done, it needs to still make sure that Notepad works. So it still needs to jump back to the original code. So the special data OEP is where the virus stores the original code, so that, if the parent is injecting into notepad.exe, it needs to say, okay, I opened Notepad, I injected my child virus into there, but I'm going to copy that original entry point and put it in data where the virus can find it. So you got your kill switch counter, which when it gets greater than 1, the virus won't run. You've got your OEP, and then this is the virus body. And this is specifically inject me. So all of the code which makes up the function inject me, that's the virus body, and that code accesses these 2 data values which it assumes will have been put there by its parent. And so in this initial baby's first phase.exe, we have to play a little trickery in order to make sure those data values get set the way they should be. That's just what that is right there. So back in inject me, the first thing that we're going to do is we run some code which is basically going to say, this is some code executing, this is code which will eventually be executing in the context of some virus injected into Notepad or whoever else. What this code, all this code is trying to do is it's trying to find where is my special data immediately before me. So it knows that at some point, oh, yeah, this is, sorry, not exactly accurate here. There's a little function above this called find base address, find kernel 32.pl. Got a little helper function which comes right here. So there's some helper function, but when we get into the actual inject me, what this code right here is doing is it's saying wherever my code is running in here right now, find that address. And how it does that is through what I call a call 0. Those 5 bytes, E80000, that's a call instruction that's saying call to an address which is 0 bytes after the next address. And so it's basically calling the next address. But the side effect of the call, right, is that it pushes the address of the next address onto the stack. So functionally, all a call 0 does is it's like push the EIP of the next instruction. And if it pushes the EIP of the next instruction, and if that instruction is somewhere in here, we can say that from that instruction, there's some hard-coded value before that I can find my kill switch counter and my OEP. So this basically says, all right, I'm going to push the address of the next instruction, and then I'm going to pop that address into EAX, and then I'm going to subtract hex 40 in order to get the address of kill switch counter. So this is just one way. I said before, position independent code is a bit more complicated because you need to find stuff dynamically. So the virus can't just assume that it's going to be at some virtual address because it'll be injected into a variety of different virtual address spaces at different offsets into the binaries. So it needs to go ahead and find its own data so that it can write that data, so that it can write a copy of this data to the next virus, right? So the original parent set up some values for the child, but when this child virus is running, it needs to copy all of this into the next child, right, the grandchild, and therefore it needs to know where those are, it needs to check those, etc. All right. So first thing it does is it says, if special calculated data, so this is the kill switch counter, it's the 0th entry of that array. If that kill switch counter is greater than 1, just exit out by calling to the original entry point. So, and actually, now that I think of it, that is, no, that's fine. Okay, good. Yep, so basically it's just saying initial check, if kill switch counter greater than 1, just exit out, go to the original executable. All right, second thing it does is it calls find kernel32.exe. This was the special helper code, and we already saw a variant of this. When did we see it? In the IAT hooking lab. So I said there was this like special way that you can dereference through data in order to, we go and we start at this FS30 in order to find eventually the list of loaded modules right now. So again, over to the board, please. I said there was like a linked list where in every process's address space, there's this linked list that says, like, let's assume that this thing got injected into hello world. There's a linked list that says, this is hello.exe. And then there's some link to, this is ntdll.dll. Then there's a link to, this is, well, that's not going to fit, kernel32.dll, etc. And so there's some linked list that the OS keeps that says hello.exe has in its module address space ntdll, kernel32.dll, user32.dll, etc. And so this little snippet of code is just assuming the existence of a linked list, and it's assuming that kernel32 is the second one in it. So it basically finds this base of this linked list, follows the link once, follows the link twice, goes into this data structure, and somewhere in here, there's an image base type thing. So it says, in this current process's address space, kernel32.dll is loaded at, 7C9000000 or whatever it is. This is not a PE header. This is just some extra data structure that the OS is keeping track of. But what the virus code does is it says, I need to go find the base address of kernel32 because I'm going to go parse its exports. And I'm going to find the export for opening files, reading files, writing files, etc. So that's what the little find kernel32 does. All it does is it just parses some data structures and finds the base address of kernel32. So the return value from this is that we expect in EAX that there's going to be like 7C9000 or whatever. All right, so that's find kernel32 base address. And so we call that right there. We got kernel32 base address. And then what we do next is, just like in the import address table thing, we're going to do some casting and whatever. And so we cast that to a DOS header, and then we access the ELFA new, and that's the offset to the NT header, right? So that's the offset to the NT header, but we need the base address plus the offset to the NT header in order to get the actual virtual address of the NT header. From the NT header, then we say, okay, treat it like an NT header, go to the optional header, go to the data directory, go to the export thing, go to the virtual address. That'll give me the relative virtual address of the export information. And so if I add that to the absolute virtual address of the base address plus the offset equals, I am now at the export directory. So the point is this thing just walks its way through the PE structure of kernel32.dll in memory in whatever process it happens to be injected into. And then it pulls out, well, it mainly just wants to find the export table so that it can start walking through and trying to find the RVA of the functions it's trying to import. So here, right, this little chunk of stuff right here, this is me cheating basically. So I've found the, well, let me show the picture. So the virus code at this point has found the export address table. That was the table we said is a bunch of RVAs pointing at exports. And so the cheating here is that I just went and looked on my operating system and I said on my operating system, open file is ordinal blah, right? And so I just hard-coded those ordinals. So the virus is, you know, if any of those ordinals change, then the virus will be, will not run. But the point is, at this point, the virus has walked to the export directory. It's found the address of functions table, and it just says, okay, well, I'm going to assume that write file is index 41, and I'm going to assume that close file is index 47, and whatever else they are. So the virus is walking through the exports information, trying to find specific functions. It wants to find the specific relative virtual addresses, which it will then add to that base address that it got, the 7C9 whatever, and add them together and get an absolute virtual address for a function that it wants to ask. Yes?
So those are system calls. And
they're not system, well, yeah, actually, we'll say they are. They're the user space side of the call to kernel, yes. So kernel32.dll is implementing the users, no, is that true? Yeah, I think that's true. You know, it's the end of the day, I'm brain dead. So I'm going to say, yes, that's true, and if it's incorrect, I'll go back and edit the video to make it incorrect. So yes, kernel32.dll is the, you'll hear like a voiceover. Kernel32.dll is, kernel32.dll is the user space side of a call to some kernel function. And that's because only the kernel can open files and only the kernel can read files and stuff like that, because only the kernel can access hardware. So all this is just a bunch of hackery to say, this multi-use int pointer right now, I just happen to have like a spare variable that I keep reusing. It points at the base of that export address table, and I'm just assuming that index 31, hex 31 is close handle. And I'm assuming that index 4f is create file and stuff like that. So just as a quick way of finding the function addresses, I make some assumptions there. All right, so now that I've got each of these are all now function pointers essentially. So actually, well, it doesn't matter. The point is, they're function pointers, and I can call them as if they were just regular functions. So the next thing I do is I start using them. First thing I want to do is call my set current directory. So my set current directory is just set current directory, and what that's going to do is it's going to say whatever directory I want, set that as the directory so that all file accesses are relative to that directory, right? So I'm going to set the directory to C:virus target, because basically I want this thing to only ever open files within C:virus target. So what we're going to do is we're going to say start at C:virus target, and every .exe you try to open will be relative to that, but we're not going to like traverse any directories or anything. So this is, now this is all just hackery in that basically, and this again is stolen from a trick Corey reminded me of. We said normally we don't like pass strings on the stack, but in this case what we did is over to the board, we said like, I'm going to push, so if this is the stack, what I'm going to do is I'm going to push chunks of a string onto the stack, and then I'm going to actually put a pointer to the string on the stack. So if this, well, I'm going to just mess this up. Virus target. Is it on the screen still? Yes, I'll just use that. All right, so this is like, I'm going to put this in big endian order so that it's easier to understand. But this is basically like the trailing slash. And then this is like null, null, null. And then this is like GET for the target, right? GET slash, so again, I'm reversing the order from what I have up there, but that's the GET from virus target. And the next thing is going to be S and TAR, S, TAR, and then this is going to be Vira, right? And this is going to be C://. Right, so I pushed the literal string onto the stack, C:/virus target terminated with null characters. And then at the point where I get right here, I'm going to push ESP. So that last instruction, push ESP. When I execute that instruction, ESP is pointing right here. And when I do that, this value right here is basically pointing right there, and ESP is now pointing down here. So basically, when I push ESP, I just basically am pushing a pointer to this string which I just pushed onto the stack. So it's like my virus doesn't have a .rdata section that it can store strings in all nice like. So I just throw a literal string onto the stack, put a pointer to that string, and now I can pass that pointer into set my current directory, which just wants a pointer to the directory which you want to set as the current directory. So that was the first instance of me just calling my own function pointer in order to set something. Next, I'm going to call find first file. Oh, here we go. I have this C pseudocode. The next thing is just going to call my first file with a string of star.exe. And so it's saying we already set the directory to virus target, and now we're calling find first file, which is just going to find all of the exe files in that directory. So the star.exe, that's a regular expression saying, you know, give me all of the files that end in .exe in whatever my current directory is. So again, I play the same trick of dumping a string onto the stack and then pushing the pointer to it down about here. And so that's, again, just to find all the exes. Next, what we're going to do is we're going to loop through each of those exes, try to open the file, and then infect the file. So we're going to do while one. Sorry, one thing I have to say here is, yeah, no, I don't have to say it. Basically, what will come back from this find first file, it's going to get you the first file, and so it's going to actually give you back a name of, like, this is the first.exe file that I found, and it'll give you the attributes. So first I just check the attributes to make sure it's not a directory, that it didn't, like, find a directory named .exe, which, see, I think that can happen. Yeah, And so if we found that this is a directory that we opened, then we skip to the next thing by calling find next file. So we said, I want to go to the next file. Otherwise, if this is not a directory, then I call my create file, which is just how we open files on Windows. Create file. I know, psi. And so we open the file, which was passed back to us by either find first file or find next file. And if we succeed in opening it, then what we're going to do is we're going to start reading some data out of it. So we call my read file. And we're going to read hex 1000 bytes. So we're going to start at the beginning of the file. We're going to read hex 1000 bytes because we want to look at the section headers and stuff like that for the thing we're infecting. So let's say we opened up hello world, or let's say we're about to infect hello world. We read in the first hex 1000 bytes, and we can start parsing its PE headers and say, okay, where should I tack this on? So actually, the virus does have even one further little sanity check. In the DOS header, so if this read file succeeded, then this buffer holds the first hex 1000 bytes of the file we're about to infect. If the buffer, so first we check if the buffer eMagic is MZ to make sure that, so this image DOS signature, that's the literal characters MZ. So M and Z, Z and M. So first we check, did this file that I even open, is it even an executable file? If not, exit out, go to the next file. If it is an executable file, if it's a DOS file, then I actually set the reserved field to hex full, or hex F001. So I take a reserved field in the DOS header, which is never set to anything, it's just set to 0. And I check, is that currently set to F001? If it is, this file is already infected, and I don't want to double infect it. So this is just my sanity check to say I should not ever double infect a file. So if this thing is set to this value, don't infect, skip to the next file. If it's not, keep on going. All right, so if we keep going, then we take the buffer, and we're just going to do some casting again to get the NT header for this file that we want to infect. Then we check the signature to make sure it's, right signature. And we make sure that it's got the executable characteristic to make sure it's an executable further. And then, okay, so now we're really actually going to start modifying the headers. We have a local copy of the headers right now. We read in the hex 1000 bytes. We're going to take our local copy and we're going to start modifying the headers. And then eventually we're going to write that back down to the file on disk. So the first thing I do is I set this hex F001 in order to say this is something I've infected. I want to make sure that further instances in the future don't infect it. And the next thing we do is we go and find the characteristics for the section header. So we actually go to the last section header. What it's going to do is it's going to expand the last section header. So no matter what it is, doesn't matter whether it's relocations, resources, anything else, we're just going to go take the section header and increase the size by the size of the virus, so that when we tack on our virus to the end of the file and when the OS loader is reading that section into memory, that we're actually going to get that virus code into memory as well. So first thing we need to do is make sure that if it's set to discardable, so if that last section, it's probably going to be like a resource section or something like that, which I said can be set to discardable, and therefore the OS loader will load it up once, but then it'll drop it out and throw it away. So we turn off the discardable characteristic of the section for that last section header to make sure that our virus doesn't get kicked out of memory. And then we also, just to be safe, we set the characteristics on that section to be, read, write, execute, and code to make sure that, my code can actually execute, that it doesn't get mapped into memory as non-executable. So we're just starting to pave the way for the virus code there. Expand the last section, make sure it's writable, executable. And then, right, and so we don't actually expand it until right there. This is where we actually take the section header and we increase the size by hex 1000 bytes because that happens to be, enough size in order to fit our virus. I think the virus is hex 500 and something bytes. But right here, we actually create a copy of the original entry point. So before we overwrite the entry point in the headers to make it point wherever we think the virus code is going to be, first we create a copy so that we can write that copy into that original entry point data structure that's tacked onto the front of the virus. So create a copy for later on. And then in our copy of the headers of the thing we're about to infect, just go ahead and, calculate the end address plus some little offset plus this hex 30, so basically right here where we're calculating the new original entry point, we know that this virus is going to be tacked on to the end of the code, but we can't just calculate the address of the last piece of the original thing because that would point us at the data. So we do the actual plus 30 here in order to say point the header all the way down to here at the very beginning of the virus code. So that's just a miscellaneous little fix up there to make sure that we actually offset the correct amount. And so another little miscellaneous thing we have to do is we have to take the size of the image and make sure that we said the size of the image is the total size you're telling the operating system to allocate for the entire file. So if the original thing were to say, here's hello world.exe and it only goes to here, you need to make sure you tell the OS loader you need to have enough space to include my virus as well, because otherwise it will not have enough space. And I found this out the hard way, right? So size of image really does have to be the full size, otherwise it's going to work. All right, so having modified all those section headers in our local copy that we had read in from disk, now we're just going to write that back out to disk. So first thing we do is my set file pointer. That just sets the file pointer back to the beginning of the file. and then we write back out our hex 1000 bytes of our buffer. So we read in 1000 bytes, parsed through those header information, modified it in anticipation of the modifications that are going to be necessary for the virus, and now we write it back out. We have not yet written the virus to the file. We've just read in a file copy of the headers, modified it, and written it back out. So now, after the file write succeeds, now it's time to start actually writing the copy of our virus to the file. So what we do is we just create a buffer, and we use those rep stos and rep moves instructions that you learned about in the intro x86 class. So this will be good review for you later when you're reviewing this code, to go back and understand why a rep stos is sort of like a mem set and why a rep moves is sort of like a mem copy. But anyways, we mem set our buffer to 0, and then we mem copy our virus into the buffer. Oh, sorry. Now this is the key point. This is the virus code eventually will be, it'll be running somewhere here. When I say we mem copy ourselves into the buffer, I should say the virus allocated hex 1000 bytes on the stack for this buffer, basically. And the virus is running here. It's got a buffer on the stack. And now the virus mem copies starting at its own kill switch, reading its total size of itself, and it copies that into a buffer on the stack. And it's going to take that buffer and it's going to write it out. So the question is, why did we use a buffer on the stack? Because otherwise we'd have to go out and, get ourselves a malloc or get ourselves a heap alloc or something like that. So it's just easier to just allocate hex 1000 bytes on the stack. So we copy ourselves off to a buffer, and then we're going to write that buffer to the end of the file. So we copy ourselves to the buffer, and then we do two little fix-ups. So actually, I'm going to run out. So over here on the stack, we allocate a hex 1000 byte buffer, right? And then we copy ourselves to that buffer, however big that is, right? Because we're only like however big we are. Well, I'm just do it like this, right? So this code in here starts up here, copies this data all over here. So this is a copy of the virus. Now what this line right here is doing is it's saying copy of original entry point, and it's writing it to the buffer of 1. So right now it's treating the buffer like it's a D-word sized array, and it's saying index 1, which is this right here, set that to a copy of the original entry point. So write, hello.exe OEP. So this is the original entry point. We're writing that into our buffer, and then we're going to write the kill switch counter to be equal to 1, or basically whatever our current one is plus plus. So we say whatever our current one is, add 1 to that, and then write it there. And then now this buffer is set up. It's got the data, and it's got the virus, and now we can go ahead and write this to the end of the file, because the file headers are all set up the way we want. Right, so this is copying the original entry point for the executable we're infecting. This is copying our own kill switch plus equal 1. And then finally, we just tear down, close out, close our handles. Or sorry, we close the handle, then we reopen the file. And then once we've reopened the file, we set the file pointer to the very end. And we actually, I think we opened it in append mode. So we were opening the file in append mode. We set the file pointer to the end just to make sure. And then finally, we write out our buffer, which contains our new copy of the original entry point and the kill switch and the actual virus. So do that, and then we close down. And then finally, what we need to do is we have to actually clean up the stack. So what we're doing now is the virus has run to its completion. So the virus has run to its completion. It's down here somewhere. And it now wants to jump back to wherever the original entry point would be for whatever code it's currently infecting. So what it's going to do is it's going to take the original entry point, move that into a register, because it's not going to be able to access that data anymore after it cleans up the stack. So it's going to copy the original entry point into a register, clean up the stack so that it gets rid of all of its local buffer, gets rid of all of its local variables, everything else. All of that goes away so that the stack is back to the pristine condition that it was when it got called. And similarly, that's the exact same condition that the stack should have been when the original, infected program got called. And therefore, once it does that, it can, move that into a register and then call leave, which we know just destroys everything on the stack. It just takes the ESP and puts it up to the EVP. And then we just call jump EACX, and that jumps back to the original thing. So that was the long, drawn-out explanation, so that you at least have some context when you're looking at it later. So now let's see this thing actually run and see the proof pudding of its actual infection of files. So what we're going to do is we want to first get some copies of Hello World that we can infect. So actually go ahead and click on Hello World, set that as the startup project, and then just right-click on it and say Build. It looks like mine's already built. So then go back out to your desktop, go to Code, and then Life of Binaries, Life of Binaries. And under the debug under debug, you should now see hello.exe. Okay, so you've got Hello World in the debug directory. Go ahead and open a new window, and you can hit like Windows key E, and go to the C directory in a separate window. And we want to make a folder C:virus target, right? That's where the virus will only infect files in that location. So make a new folder, virus target, in C:. Yep, no space. All one word, virus target. And then just copy Hello World over there, and then actually copy some copies of Hello World. Oops. Make some copies of it, like so. Actually, and then I'm going to, just for simplicity, due to alphabeticalness, I'm going to call this instead Hello World 2 and Hello World 3. Because that'll make it easier. Interesting. All right, so we're going to start executing the virus now from baby's first page. You should have, 3 copies of Hello World in C:virus target. And so we go back to Visual Studio. And we right-click on baby's first page again, and we set it as startup project, so that we can actually start executing it now. All right, so in baby's first page, down in main, I want you to set a breakpoint on inject me by clicking to the left of inject me, and that'll have that little red dot show up. Can't see it. Where's that thing? All right, so now you should have a breakpoint set to inject me. So now you can just go ahead and right-click for build. And this is going to compile this parent virus. And then you can go ahead and click on debug and start debugging, or just hit F5. All right. So then the virus will be running, and it will be stopped before it ever calls inject me. Yep, got it. And so the key point here is we set the breakpoint outside of the actual inject me code, because if we set the breakpoint inside the inject me code anywhere, this is, I'm telling you this for if you try to test this later. You don't ever want to set a breakpoint inside of inject me, because when it gets to that phase where it like copies itself over into the buffer and it copies that buffer to the thing it's going to infect, if you have breakpoints inside of your copy that you're injecting, those breakpoints will be hit when the virus is run within the infected executable, and that is not a good thing, because there will be no debugger there in order to catch those breakpoints, and the thing will just crash. So to make your virus actually run without crashing, don't ever set any breakpoints, or at least remove them before you execute the code which copies itself. So now we can step into inject me. by seeing this little arrow into, it should say step into when you mouse over it. And at this point, you can now just use the step over. And, if we want, well, so, is that? Right, yeah, I mean, it's going to skip all of that initialization. Well, it's not even initializing any of those, I don't think. So it's just the definition of a bunch of local variables. So the first place we're stepping to right now is this, and I'm saying that this is actually a call instruction. It's just me manually writing the call instruction. So as we saw in the intro class, when you're debugging in Visual Studio, you can right-click and go to disassembly. If you do that, you will indeed see that it says that these E80000 is a call. And specifically, it's calling to 401040, which is the next instruction immediately after it, right? It's calling to an address, which is the address of the instruction immediately after it. So it doesn't skip over any code or anything. All it does is just go immediately to that address and simultaneously push the address of the next instruction. So all it really does is just push the next address. So that's a fun little trick that you can use. All right, so anyways, I'm not going to go through all this code again with you, right? I'm just going to let this thing run at this point. And what we expect is, if this thing is correctly infecting executables, if you open up a command window and you go to C:virus target, and you do dir, in order to see the file size of each of these things, they're all the same file size, right? They're all copies of each other. But when the virus is actually injected onto the end of the executable, right, the file size should go up. So if this thing's successfully infecting, the file size should go up. But of course, that doesn't mean it'll successfully run. So first, let's just go ahead and hit this continue in Visual Studio to just let the thing run, infect as will. And so it does that, and then it says exited with code 1, so that's good. That told me that it succeeded. So we go back to that command window, and if we do dir again, we now see that hello world.exe has increased its file size from 28 whatever to 32. So there does seem to be an increase in file size of hello world.exe. But if I try to run it, oh, never mind. It does actually run. So on my system, it was not running things that did not have correct checksums. And the spec says that the checksum isn't technically required to be correct, but I thought, well, if it's never running without correct checksum, it must be required. So anyways, on this system, it's working just fine. So if I do dir again, we see I just ran hello world, but hello world 2 just got bigger. Right? So that's kind of interesting. That means that I did successfully virally infect hello world ran, and it went ahead and it infected hello world 2. Now, I'm claiming, so I said baby's first phage is the parent, hello world is the child virus, and now hello world 2 is the grandchild virus, and I'm claiming that this one cannot actually infect anyone. So if I run hello world 2, we should not see hello world 3 increase in size. And we did not see hello world 3 increase in size because hello world 2, it ran, it printed out hello world, but it immediately, the virus code gets into the virus body. Over to the whiteboard, please. So, if this code is in, hello world 2, it gets here into the virus body, and the first thing it does is it checks the kill switch counter. And that kill switch counter keeps getting incremented each time that this thing virally infects another thing. So it checks its kill switch counter, says, greater than 1, immediately jump to the original entry point and just run the normal hello world code. Now, hello world 2 can't infect any things because it's a grandchild, but hello world 1 could still infect this next thing. So I hello world 1 it. Hello world 1, so the thing is not so safe right now that the children can't keep infecting things forever, but at least the grandchildren can infect things. So that is the virus lab. We will do a 5-minute break. Ask any questions you want right now. But otherwise, that's it for the virus lab. It's, again, one of those cases where definitely going to want to go back over it, understand it to more detail. But the key point is that you're going to see a lot of code parsing through data structures in the imports, exports, whatever. Well, just the exports, rather. So, yes, question?
Well, mine isn't actually working.
Is not working? That's tough. We'll try it on yours in a second. I'll show the, because, you know, like I said, it doesn't work. It didn't work in my VM that I was developing this on. So I will show, when you get back from the break, I'll show how you would fix up the checksum to see if that will actually make it work. So got some questions on that. Yeah, so Grant said this is only specific to Windows XP 32-bit. Yes, that's correct. And Chris, go ahead with your question.
Okay, dumb question. You set it. Did you set the breakpoint at inject me in the?
Yes, I did set.
Okay.
Right, I set the breakpoint at inject me in baby's first phase.
Great. Sorry about that. Thank you.
Right. So you don't ever want to set a breakpoint in the body of this inject me, because if you don't remove that breakpoint before it copies itself to the buffer, that breakpoint will still be embedded in there. Because we said in the intermediate x86 class behind the scenes, that breakpoint is really just putting a hex CC in there. So, all right, any other questions? Yeah. Question? No? If you left that in there, then when it's going through, the hex CC is really just an interrupt 3 instruction. So when you do that, hello world would basically, well, I can do it, right? So let's do it. Let's put a breakpoint in the middle of our inject me, and then let's run baby's first phase and see what happens to hello world when it tries to infect hello world 2. Right? I'm going to get some new copies of them. I should have made backup copies, but there's my hello world. There's my virus stuff ones. So I'm going to make some new copies of this.
Virus mitigation.
That's right. See, it's disinfecting the virus. You know, I could actually, so I could also go in and I could pre-disinfect it by setting that reserved field to hex full, right? And then it would never actually infect anything. But let's set a breakpoint in there and run it. So I'm just going to set like a breakpoint right here, for instance. Well, let's even put it farther down. Let's put it right there or something. All right, so I got a breakpoint randomly wherever in here. I have this breakpoint. I'm going to let it run to the breakpoint. I'm going to let it run past the breakpoint. It's still exited with code 1 telling me it succeeded in infecting the thing. The only problem is it's got that one breakpoint embedded in it. So copy of copy is infected right now. And when I run that, I expect it's just going to crash, basically.
But one thing is,
Stupid DOS.
not printing hello world stuff.
Right. Well, it didn't print out hello world, that's for sure, right? I believe it basically just silently crashed at this point. Although I would have, well, if I open it in a debugger, then that would tell me it crashed. But since it's a command line thing and it doesn't, you know, have any sort of GUI opening up in order to see, like, exceptions, I believe it basically just crashed.
What other question?
Are you, okay, go ahead.
Yeah, when you take hello world, do you take the entire folder and copy it over?
No, I was just copying the actual executables. So see, in SQL and virus target, there should only be some executables that you want to actually infect.
Okay, thank you.
Question? No?
Mine seems to have infected other files, but it didn't actually print hello world.
It infected them, but it didn't print hello world. I'd say that's probably another case where it's not running due to the section error, due to the checksum. So did anyone else have theirs, it infected them, it increased the sizes, but it wouldn't, wait, yours did it twice? Or you ran, did you run baby's first phase multiple times, or did you run copy of hello world?
I ran.
You ran hello world.
Hello.
Right. And then that infected, that increased the size of the next one, but it just didn't print anything out? Interesting. I don't know what's up with that. Did anyone have a case like David where it simply wouldn't run?
I got it working. I just switched to debug instead of release.
You switch to debug rather than release?
Yeah, so
Oh, you know what that probably is?
yeah, absolutely.
That hard-coded offset where we said, like, at the very beginning when it finds its data, it just hard codes a subtract in here. Debug versus release, it's going to change up the size of padding and stuff like that. So yeah, it definitely has to be the debug version of Baby's First. So slide 10 in Life of Binaries 4 is saying, copy the stuff to the virus target, run Baby's First phase in debug mode. It even says debug mode. You're not following instructions. And then you eventually are supposed to go in and fix the checksum, at least that's what was necessary on mine. And then you can, well, we could step through the virus actually in WinDebug if we wanted. So you can infect a file and then open that file in WinDebug and set a breakpoint at the address of entry point, and you should start seeing code that looks like the virus code from inject me, right?